Alright, so we're going to be doing problem number 27, which is the first red problem from chapter 8. And what I have written already is what the problem gives us. So here we go. We have a uniform board of length L that starts with the velocity going to the right. Now it's our board starts on a frictionless surface, horizontal, and encounters some rough surface that has a coefficient of kinetic friction in between the board and the rough surface. Now the board remains the same length L, and the length of the board that happens to be on top of the rough surface we'll call x. Okay, let's get on to part A, where we're asked to find the acceleration, which is obviously in the left direction because the block slows down with its initial velocity going to the right. Everything in part A is nothing new. We've learned how to do all of this stuff before chapter 8. So if we define a mass of the whole board as m, then the mass of the part of the board that's going to be on top of the rough surface will obviously be defined by the mass times the portion of the rough that's on the rough surface over the whole length of the board. It's obviously a fraction of the mass of the part that's on the rough surface is obviously a fraction of the entire mass. And so what we have is, I'll draw another diagram where this part on the left is the part that's on the smooth surface as it's going to the right, and this part on the right is the part of the board that's on the rough surface. Now it's going that way. I'm going to draw a free body diagram. Down we have the mass. Down we have the mass times gravity, mg, and up is the normal force. If we sum the forces of the part of the block that's on the rough surface, we have normal force minus mg equals may, which cancels to 0. So our normal force is equal to m g. So Fn equals g. And to complete part of our body diagram, there will be friction to the left, and that is the only force, as velocity is to the right and velocity is not a force. Now friction is obviously mu normal force, and from what we have above here, we know that normal force is the portion of the mass that's on top of the rough surface times gravity. So our frictional force will be coefficient of kinetic friction times our partial mass times gravity. If we sum the forces in the x direction, we have friction as our only force to the left equals ma, and friction equals mu times the partial mass times gravity equals ma. The m's cancel, so our answer is A equals negative coefficient of kinetic friction times xg over L. That is our acceleration. It's obviously in the negative direction because on our we defined positive x is going to the right, and our acceleration is to the left. Okay, so that's part A. And then for part B, we'll be finding the initial velocity. Now, to do this part of the question, we're going to be focusing on work. Work equals kinetic initial minus kinetic final, which equals 1/2 mv initial squared minus 1/2 mv final squared. Okay. Now we're told that this board eventually stops, and it stops perfectly just onto the rough surface. So the distance L is the same as the distance X in part B. Our final velocity is 0, so this goes away. And we're left with work equals 1/2 mv squared. And additionally, the definition of work that's not constant is given by the integral of force. So let's from this point to this point are limits of integration. So work equals, let's call from this point to this point are limits of integration. So this point is obviously going to be 0, and this point L, and force our work is given by the integral, and our only force is in this problem is friction. So incidentally, what we have is, by systems of equations, if we set the w's equal to each other, what we have is 1/2 mv squared equals the integral of friction along these limits. From earlier in the problem, we learned that friction is mu xg over L, and then we'll finish the integration. Make these initial, sorry. We'll finish the integration, so because we are integrating this with respect to x, everything else that's not x stays constant, and then the x becomes x squared over 2, and along the limits of 0 to L, and if we simplify this further, 1/2 mv initial squared equals I'm going to skip a step here, but it's just algebra. GL over 2. And then we continue our algebra to solve for v initial. So we multiply both sides by 2, divide both sides by m, and take the square root. So our v initial equals square root of the coefficient of kinetic friction times GL. And that is our answer to part B.